Hi, this is Denise de los Santos. I'm going to be presenting via PowerPoint today, a little bit something different for sure. Today, I'll be performing the presentation on the interactive advanced concept number 6, the nuclear bomb. So my goal is to get a better understanding of key ideas, what's going on inside a nuclear bomb, and what are the important components of chain reactions in order to initiate nuclear fusion. So, in order to get a better understanding, I'm going to do a small introduction. All matter is composed of atoms, incredibly small structures that house different combinations of three particles, known as protons, neutrons, and electrons. At the center of each atom is a nucleus, where neutrons and protons are bound in close proximity. Most nuclei are relatively stable, meaning the makeup of their neutrons and protons is comparatively static and unchanging. During fission, the nuclei of certain heavy atoms split into smaller, lighter nuclei, releasing excess energy in the process. This can sometimes occur spontaneously, but also, in certain nuclei, can be induced from the outside. A neutron is shot at the nucleus and is absorbed, causing instability and fission. In some elements, such as certain isotopes of uranium and plutonium, the fission process also releases excess neutrons, which can trigger a chain reaction if they are absorbed by nearby atoms. Fusion works in reverse. When exposed to extremely high temperatures and pressures, some lightweight nuclei can fuse together to form heavier nuclei, releasing energy in the process. As stated in this week's video, the most difficult part of the process of building nuclear bombs is the process of separating two identical variants of the element uranium containing two isotopes. The diagram from this week's lab is a perfect example of the two variants and display the similarities. The neutrons definitely plays a major role, but also the weight of U-235 is lesser than U-238. This is less than a 2% difference, and this difference allows for the separation of the two isotopes to be possible. The isotopes U-235 is usually selected by atomic scientists because it readily undergoes fission. Fission occurs when a neutron strikes the nucleus of either isotope, splitting the nucleus into fragments and releasing tremendous amounts of energy. The fission process becomes self-sustaining as neutrons produced by splitting of atoms strike nearby nuclei and produce more fission. This is known as a chain reaction and is what causes the atomic explosion. When U-235 atom absorbs a neutron and fission into two new atoms, it releases three new neutrons and some binding energy. Two neutrons do not continue the reaction because they are lost or absorbed by uranium-238 atom. However, one neutron does collide with an atom of 235, which then fissions and releases two neutrons and some binding energy. Next, I'll go ahead and have a picture or a diagram that's going to be better at showing and explaining this. So both of those neutrons collide with U-235 atoms, each which fissions and releases between one and three neutrons, and so on. This causes a nuclear chain reaction. So this is the diagram I was discussing about earlier. As shown in this diagram, when U-235 atom absorbs the neutrons, it breaks into smaller atoms plus some number of neutrons. This splitting or fission also releases atomic energy that can produce electricity, or in this case, an explosion. On average, such a fission of U-235 atom produces about 2.5 new neutrons. If all released neutrons are absorbed by U-235 atoms, an exponentially growing chain reaction sets in, with the number of atoms involved growing from 1 to 2.5. After 10 generations, over 10,000 atoms have fissioned. After 20 generations, over 100 million atoms have fissioned, and etc. But as depicted in the diagram, some neutrons escape without adding to the chain reaction. The one with an X on the right side near step 2, and some are absorbed by U-238 atoms, and that's the one with the X on the left-hand side on step 2, and do not produce additional neutrons to add to the chain reactions. By absorbing an additional neutron, the U-238 atoms become U-239, which is on the left side by step 2, and do not produce additional neutrons to add to the chain reaction. The important point here is that it does not produce additional neutrons. If on average each fission leads to more than one additional fission, the chain reaction grows exponentially and releases large amounts of energy. So lastly, the U-235 is the valuable isotopes from a nuclear weapons or nuclear power point of view because it can serve as the primary fuel for a weapon or power plant, while U-238 cannot. Atomic forces within the nucleus are much stronger than chemical forces. U-235 is an atom bomb, therefore liberates much more energy than exploding the same mass of TNT. The bomb used on Hiroshima contained approximately 100 pounds of U-235, yet packed the explosive power of 15,000 tons. That's 30 million pounds of TNT. In the model, the bomb has two separate compartments, one filled with 40% of uranium-235, which is the target, and the other back end is 60% of uranium-235. An explosion at the back end drives the projectile forward to the tip, initiating a nuclear explosion. So that's pretty much the end of my PowerPoint. I do appreciate your time, and I hope that you enjoyed it.